All right, so at the end last time I said we were going to talk about Thomae's function. This is one of my favorite, maybe my all-time favorite weird example of a function. Thomae's function. This is that one that where the graph kind of looks like this. This kind of a thing, where all the irrational values are 0. So the definition here, if you recall, is f of x equals 1 over n if x is in Q, x equals m over n in lowest form. So if it's rational, you just sort of throw away the numerator, turn the numerator into a 1. And if it's irrational, the answer is just 0. If x is not in Q. All right, this is Thomae's function. I said at the end last time, I want to discuss where is this function continuous and where is it not continuous. And the answer is all of these, like individual points, it's not continuous right there because like the curve doesn't go through here at all. There isn't really a curve at all, but whatever it is, it doesn't go through this point. Like all the nearby values are way down here. So it's discontinuous at this point is 1/2. It's also discontinuous at 1/3 and 2/3 for the same reason. In fact, any one of these individual rational points are always discontinuous at all of those points. So I want to show, this I want to do in some amount of detail. We'll show that f is discontinuous at all rationals, but continuous at all irrationals. I wrote all. I meant at all. Continuous at all irrationals. All right, very strange. It is actually continuous at the irrationals. The irrationals are the ones that all go down to 0. But when I say it's continuous at those values, I guess it means, what it means is not only is the irrational value down at 0, but all the nearby values are also near to 0. That's what we would have to demonstrate to show that it's continuous at all irrationals, right? So let's just talk about these two things separately. You got a question?
It's like, what if you have an irrational number at 0, but it's like really close to, like the x value is really close to 1.6 up in the air?
Yeah, like some irrational that's super close to 1/2.
Yeah.
Yeah. It's still continuous there. Is that outside? I hear like a radio or something. All right. Oh no, it's a tray or one of those things. Sorry, it's not a radio. If you have an irrational really close to 1/2, it's not close enough because there are other numbers even closer where the values of the function will be close to 0. We'll see, I think. See if you're convinced by the proof. Let's talk. So I want to talk about each of these two things. This is a very good thought, though. Let's talk about why is it discontinuous at all the rationals first. I think that's a little bit easier. So let's talk first about let C be rational, and then I want to show f is discontinuous at C, right? Anybody want to recall how, anybody remember how we show something is discontinuous? I know it's been over the weekend, and anybody already did the homework? No, I know. Something is not continuous. This, the typical way to demonstrate this is using sequences, right? You show that there is some sequence which approaches a certain value, but the values of the function of that sequence approach a different value. They do not approach what you want. So we're going to use sequences. what we want is we'll find a sequence, say xn, which converges to C, but f of xn does not converge to f of C. All right? Because if it is continuous, it means whenever you have a sequence, the f of that sequence converges to the f of the limit of the sequence. But this is how you would show something is discontinuous. You find a sequence which approaches C, which, remember, that C is rational. But the f's of that sequence do not approach the f's of C. So just so we can say something specific, let's say that C is, we already know C is rational, right? So I can say, let's say that C as a fraction is m over n. So f of C is 1 over n, right? Can anybody suggest, is it true that you can find a sequence of points approaching C where the f's of those values do not approach, I guess in this case, 1 over n? Now the only thing really we have to work with are rationals versus irrationals. I mean, we don't really know anything specific about these numbers here, the 1 over n's or whatever. So I think when you're trying to think of this sequence, you should primarily be thinking in terms of rationals versus irrationals. Any ideas? Remember, when you plug something into f, if it's irrational, you always get 0. If it's rational, you get 1 over n, where n is the denominator. I would actually, we could think about the picture. Like, what if C is this point, 1/2? Can you find a sequence of numbers that approach a half, like along the x-axis, but their y values don't go up here? I think, in fact, I could find a sequence of numbers down here where their y values are always 0. How would you do that? I see some nodding. Yeah.
You do like something where it's like 3 over rad 2, 2 over rad 2, 1 over rad 2. So like the top number is decreasing and the bottom two is increasing.
Yeah. I think I was going to be less specific than that, but you could choose a sequence of irrational numbers down here that approach, say, a half or whatever, so that when you plug the values in, you're just always going to get 0, and it's never going to go up there. That's what I want to say, something like that. We got to find a sequence approaching C. So I'm going to say choose a sequence. Now you could try and be specific. This was a good idea that Joe said, but I think I'm going to be less specific about it. Choose a sequence of irrationals xn approaching C. Even though C is rational, it is possible to find a sequence of irrationals that approach that value. If you do, I'm not sure exactly what he said, but maybe like C plus root 2 over n. By my general strategy of always use 1 over n, but I want it to approach C, so I use C plus 1 over n. But I also want it to be irrational every time, so I use C plus root 2 over n. This makes it so that they're always irrational and they approach C, all right? This is what I choose for xn. I think that's something like what you said, right? And then, so is it really true? That's my sequence which approaches C. Is this actually true? F of xn approaches f of C. Then what is, sorry, I'm off the bottom. What is f of xn going to be? You plug it into the function, what do you get? Yeah? 0. Yeah, these are irrationals, so you're going to get 0 every time. And so f of xn, the sequence, approaches 0. Not C. Approaches 0 because the value, like as a sequence, it looks like 0, 0, 0. It's just 0 every time. So it approaches 0. And that is not equal to f of C, right? Because f of C is 1 over n, which is not 0. So that's the demonstration. What we have to show is f of xn does not approach f of C. And it don't, because f of xn approaches 0, but f of c is something else, not 0. So this demonstrates that it is discontinuous at all the rationals. You can always choose irrationals which approach any rational. When you plug them into the function, you're going to get 0 every time. But that does not approach the actual value of the function, which is 1 over n. Right? That was the first part. The second part, continuous at all irrationals. All right. I know this is kind of hardcore to start off the day with, I know. Start off the end of the day with. And it's at daylight savings too. Probably all totally jet lagged or whatever they call it. Okay, for this part, actually you can't use sequences to show that it is continuous. You just got to do the thing with the epsilons. So I'm going to say let C be irrational, right? And then we're going to show that it is continuous at C. So f is continuous at C. What do we do for that? We got to say let epsilon greater than 0 be given, and then we'll find delta greater than 0 such that. By the way, I meant to remind you before, our next test is a week from Friday, so that's a little something to look forward to. Let epsilon be given, we'll find delta greater than 0 such that 0 less than absolute value x minus c less than delta implies absolute value f of x minus f of c less than delta. All right. Okay. Now this one actually is very hard to write this proof in the way that we usually do, which would be to just sort of start with this and simplify, just because the function definition is so complicated here, you can't really plug in for f of x in any meaningful way. Yeah, sorry. Delta both places. I wrote that as I was saying our test is going to be next week. Don't do that on the test. Thank you. Like I was saying, you actually can't get very far by simplifying here, although there is one thing that I can do over here. Anyone see one thing you can do to simplify something over here? Yeah? F of c is 0, right, because c is irrational. That's part of the definition. F of c is 0, but that's really all you can do. So this, I can say since c is irrational, this means just that, f of x less than epsilon, right? All right, but actually there's not much more that you can do here. So this one, unfortunately, you can't follow the standard approach to these kinds of proofs that we usually do, where you would just kind of plug in the definition for f of x, because you don't know if x is rational or irrational. All right, but anyway, here's how you want to make this argument, and this may address your question from before. I don't know. We'll see. We have this irrational number c, and since c is irrational, all values, I'm going to say, can I say, I didn't mean to say values, all points very near C have large denominators. All points, I should say, I mean rationals. Sorry, I keep changing my mind here. All rationals very near C have large denominators. Why is that? This is a non-obvious fact, but once you begin to think about it, you will agree. For example, if this is sort of a little sidebar, but like if you imagine C is root 2, which is 1 point whatever. Did I write this down? No. I didn't write this down. Can I use pi instead then, just because I know more digits of pi? It doesn't really matter. This is 3.1415. I don't know much more than that. If C is an irrational, I said all rationals very near C have large denominator. What do I mean by that? Is like if you want to be really close to this number but rational, I'm talking about some number like 3.141. Well, this has dot, 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 right? But what if I just ended at that? 3.1415 exactly, right? This is rational near pi. But this, it's kind of like, because it's so near pi, this has a very big denominator. This, if you write it as a fraction, is this, 31415 over 10,000. Right? And that fraction can be reduced a little bit, but not a lot. Right? So this, I mean, as written, it has denominator 10,000. Now you can factor out a 5, but probably not much more than that. I don't really know. But this, even when it's reduced still has big denominator. Right? And if I wanted it to be even closer to pi, I would have to take more decimal places, and then the denominator would be even bigger, right? The closer you get to pi, the bigger and bigger the denominator is going to have to be. This is the fact. You can also think about it the other way around. You could imagine, well, how close could it be to pi if you want the denominator to only be, say, 2, 3, 4, or 5? The answer is you can't get that close to pi using only those denominators, because those are only like up to fifths, things with fifths. That can't get very close to pi. What if I go up to things with tenths? No, you can get a little closer to pi, but still can't get super close because tenths is only so small, right? Using certain denominators, small denominators cannot get you close to any irrational numbers. Right? This is a true fact. So what we can do here, just to write this is the basic idea which leads to the whole epsilon and delta proof. But here's what I'm going to say. I said informally here, all rationals very near C have large denominators. I'm going to say it this way. I have to say what delta is. I'm going to say choose delta so that all rationals within delta distance of C have denominator greater than n. N? I mean 1 over epsilon, sorry. I choose 1 over epsilon just because it's going to make the rest of the proof work. Because I have seen the future of this proof. I'll call the denominator n. That's what I meant. You know, when we write these rationals with Thomae's function, the denominator we always call n. So I'm going to choose the delta to be so small that all the rationals near C have denominator bigger than 1 over epsilon. All right, and no matter how if epsilon is really small, this is going to be really big. But no matter how big that number is, it is a fact that all the rationals within a certain distance will have super big denominators. So you can do this. All right. Now you might ask, as he did before, well, what if this value of C is already really close to a rational, like 1/2? Then I would just say it's still possible to choose your window so small that it excludes 1/2, no matter how close you thought it was. It was already really close to 1/2, but you can just cut that distance in half, and then all the things will have super small denominators, excluding 1/2. All right. Anyway, now the rest of the proof will work out. So I choose the delta so that all rationals within delta of C will have denominator n, which is greater than 1 over epsilon. And then, so this means that if x minus C less than delta, then I can say f of x minus f of C. Remember, we simplified f of C equals 0, so this is just the same as f of x. All right. And now you're gonna have to divide this into two cases somehow, because you don't know at this point if x is rational or irrational. But it's easy enough, because if it's irrational, then this is automatic. So if x is irrational, then this here actually equals 0, which is less than epsilon automatically. So this is not, there's not really anything to show in that case. But if x is rational, that's the more interesting case. Then this thing becomes 1 over n, right? Because that's the definition of the function. But I chose it so that this n would be greater than 1 over epsilon. That means this will be less than 1 over epsilon, which is epsilon. So either way, you get less than epsilon. And that's that. This I really wanted to do at the end last time, so we wouldn't have to start off with this somewhat hardcore proof. But it definitely wasn't going to make it at the end last time. Anybody got any questions about that? This is Thomae's function. One of my favorite examples. It's discontinuous at every rational and continuous at every irrational. Great. If you ask me, I would have said that's not even possible, but it is possible. And it is true. All right, we're going to move on to something a little bit different. What I would like to discuss today is, I don't know if we're going to be able to get to the whole thing, but a classic calculus theorem. This is a little something. There are several theorems from calculus with the word value in their names. This is what I want to talk about today is the extreme value theorem. The extreme value theorem. Anyone remember what that one says? It's about extreme values. They are sometimes called the extrema. Does that sound familiar to anybody? The extreme value theorem is about the fact that the absolute extrema of a function exist if your function is continuous. So like the sort of calculus version, we're going to do a somewhat more sophisticated version, but the calculus version of this says if f is continuous on a closed interval, say a to b, then f has an absolute maximum and minimum on the interval a to b. And in the calculus class, you talk a lot about how this absolute maximum and minimum, they either occur at the critical numbers, that is the places where the derivative is 0, or the derivative does not exist, or they occur at the interval endpoints. This is something that everybody knows. I mean, the picture you should have in mind is like, you know, a picture like this. This is a little piece of a function from a to b. Where are the absolute maximum and the absolute minimum values? The maximum is here, and the minimum is here. The minimum and maximum values always occur either at the sort of peaks or opposite of peaks. The what's? The valleys, yeah, the peaks and the valleys. Or they occur on the endpoints of the interval. All right? This is the extreme value theorem from calculus. This is how, I don't want to ruin it. This is a little conundrum you can share with your friends. I don't know, have I said this to you? I don't think I've said this to you before. Maybe you already know this. This is a true fact about the state of Connecticut, our dear nutmeg state. The state of Connecticut, I learned this when I went with my kids to the highest mountain peak in the state of Connecticut, which is not all that high. But I have been to the highest mountain peak in the state of Connecticut. And I'm here to tell you, it is not as high as the highest point in the state of Connecticut. This is a true fact. The highest mountain peak in the state of Connecticut is not as high as the highest point. And I'm not talking about like somebody built a big tower or something. There's no funny business like that. Anyone, how is this possible? Yeah?
The highest point on another mountain, but that's like Mount Floyd in
Yes, it has to do with this sort of, sometimes the maximum is on the edge kind of a thing. So it's a fact actually that if you looked at Connecticut sort of like from the side, it looks kind of like this, or like the state line is here. And this is the highest point, is on the border between Connecticut and New York, but the highest mountain peak is there, which is not the highest point in the state. You can amaze your friends with this kind of knowledge. Yeah.
What was the mountain called? Was it Bear Mountain?
Yeah, Bear Mountain.
In Danbury?
Yeah, something like, yeah, up there, northwest, yeah. But there's another Bear Mountain, like right across the border in New York.
Oh.
Yeah, I think. There's another Bear Mountain in New York, which is not, it's probably higher than the Bear Mountain in Connecticut. Anyway, that's the extreme value theorem. It just says that if your function is continuous on a closed interval, then it has an absolute maximum and absolute minimum. Now, the version that we're going to talk about is like this, only not specific to closed intervals. When you see this in a calculus theorem, it is natural to think about, is this really a theorem about intervals? Or perhaps, is this theorem generally true of any closed set? Or maybe is it true of any bounded set? Or something like that. These are the things that I would encourage you to think of. I can answer, actually both of those questions are not so hard to answer. Could you do this for any bounded set? The answer is no, because for instance, if I change this into an open interval, if I consider instead of here the open interval from A to B, then there is no maximum point. You can still like draw the arrow to it, but actually that point doesn't exist in the domain. And so you don't actually reach the maximum point if you're only considering an open interval. So this theorem here, this is not true of open intervals. So what makes it true is not the fact that it's an interval, all right? Because it's not true of open intervals. You might wonder, is it the closedness that matters? Is it true of any closed set? Actually, it is also not true of any closed set, because I could take an interval like this, but that goes out forever to the right, and then a typical function will not have a maximum value. It can go up forever. So if you allow any closed set here that stretches out to infinity, then that's also not going to be true. So not true of open intervals, also not true of closed sets like, A to infinity. That's a closed set, but functions on that set do not necessarily have a maximum value, because they could just go up forever, and that would be fine. They would never reach a maximum value. All right. It turns out this theorem is only true because this is a closed and bounded set. All right, so it's not true of unbounded closed sets, but actually this theorem is always true for a closed and bounded set. Otherwise known as, there's a name for that? A compact set. Yes, this fine young gentleman apparently knows the Heine-Borel theorem, which is that compact sets are closed and bounded. So the extreme value theorem, properly stated in its more sophisticated formulation, is about compact sets. So I'm going to say if K subset of R is compact and F is continuous on K, I don't know if I've ever said, what that means is just that F is continuous for all the points which are in K. So it may have some discontinuities outside of K, but it is continuous at all the points of K. So if K is compact and F is continuous on K, then F has a minimum and a maximum value. And I'm going to I'll just write that out. Then F has a minimum and maximum value. All right. So this is the extreme value theorem written in terms of compact sets. This is a more general version than the one you did in a calculus class, which is just about closed intervals all the time. All right. Now, actually, this is another special case. So we will talk about why this is true, but actually this follows directly from an even better theorem. So I'm going to say, if you can believe it, an even better theorem is just, it's simpler to write. if K is compact and F is continuous on K, then f of k, that is the range of the function, the set of all the values you get out when you plug in points of k, f of k is compact. All right. This actually, it turns out this, if you know this is true, you can immediately demonstrate the extreme value theorem based on this. I don't think this really has a name. I would describe this as the theorem that says that the continuous image of a compact set is compact. So if you start with a compact set in the domain and you have a continuous function, that function turns it into another compact set in the range, in the codomain. All right. I want to talk about why this is true. Actually, the proof of this is pretty straightforward, and I think we'll make a nice little exercise in terms of compact sets, which will be a topic on the test next week. Let's see if we can demonstrate this. You don't really need a lot of big ideas, although you do have to remember sort of basic miscellaneous facts about compact sets. So we have to demonstrate that f of k is compact, right? Look at that f has a little curly thing on it. You can see that. We want to show that f of k is compact. Anybody remember the definition of compact? Now the theorem says that compact is the same as closed and bounded, but actually it's more convenient to use the basic definition, which is a good thing to remember for the test. I know you got another test tomorrow. Is that a... No. Anyone remember it had something to do with sequences. Yeah?
Is it that you can make a sequence that converges and the limit of that sequence is in the set?
Yes. So it's something like what you just said. It's if you have a sequence of points in the set, then it might not converge, but it has a subsequence which converges, and the limit of that subsequence is also in the set. All right. So I want to show this is compact. What that means is, i.e., if most sequences I call xn, but I'm actually going to call this yn because these are points in f of k. Like these yns are points in the range. They're not points in the domain, which is why I'm calling them y's rather than x's. Anyway, if yn is a sequence in f of k, then there exists a convergent subsequence converging to a point of f of k. That's what it means for f of k to be compact, is that if you take a sequence in there, it has a convergent subsequence which converges to a point in that set. All right? Now, where are we going to go with this? So we start with a sequence. I somehow have to demonstrate that it has a subsequence that converges, and the thing that it converges to is in the set. We don't have much to go on other than the fact that yns are in f of k. So that means every one of these points is f of something, right? F of k is the range of the function. So all of these points are f of something, and those somethings I'm going to call xn, right? Each of the yns comes from xn. So I'm going to say, since yn is in f of k, there exists a sequence xn, which is in k, such that f of xn equals yn, right? For each n. If you like to think of this sort of topologically, the way I kind of imagine this is, I have like, here's k, my compact set, and then f of k, which is the image. And f is like a thing which turns that thing into that other thing. And what we started with is a bunch of points over here, y1, y2, etc. And what I said was, since these are all over here, they're in f of k, it means they must have come from some stuff over here. And those I'm going to call x1, x2, x3, etc. Right? The only other thing we know in this theorem is that k is compact, right? That's the assumption. Anybody have a suggestion? What does the fact that k is compact, does that mean anything here? I think so. I mean, we have a sequence over here inside of k. So the fact that k is compact, what does that mean? Can you say? Yeah.
That sequence has a subsequence that converges.
Yeah, it means that there's a subsequence over here which converges, and what they converge to is in k, right? So that means, I mean, you could say something like, I can take a subsequence which is like only some of these guys, not all of them, but if I take only some of them, the red ones, then they actually converge, and I'll say they converge to x. So since k is compact, I'm going to write that in words. Since k is compact, there exists a subsequence. The red ones, which unfortunately if you're writing about this, you have to call it something like x n k, right? This is a subsequence of the xn's, such that x n k converges to x, and x is in k, all right? Okay, we're actually almost there. Remember, what we're looking for eventually is some point over here which actually these things converge to. Anybody got an idea? How could we figure out where these guys are converging to? I would say these points originally came from these guys, right? But you pulled them back. If I look, if I sort of push this business forward again, like these ones that I circled in red correspond to some of these, right?
So
Yeah.
they converge to f of x.
Yeah, these things, I mean, if you believe the picture, these things ought to converge to wherever that point goes over here, right? These things should converge to this point, which would be f of x. Now, is that actually true? I have to sort of write out this in terms of the proof. X and k goes to x, and x is in k. Is it actually true that, I wanted to say really, y and k, which of course is equal to f of x and k, is it true that the y and k's converge to f of x? This we have to explain why, although it's true. It's true for a very clear reason. Although it may, if you see it, you see it. Can I just say, since f is continuous? Remember, the sequential version of continuity says if I have x and k approaches x, then that means when I plug those into the f, they still converge to each other. That's what it means to be continuous in the sequential version. It said, our sequential version of continuity said something like, for any sequence xn approaching c, then f of xn approaches f of c. So if you ever have a sequence approaching something else, you can plug everything into the function and it will still approach what you think it approaches. This is because f is continuous. All right, and this is basically the end, right? What we've demonstrated is that y and k is a subsequence of these, and it does converge to something, and that something is in f of k because it is f of something, right? So I will just say something like that to conclude. So yn has a subsequence called ynk, and ynk converges to f of x, which is an element of f of k because it is f of something from k. So this is the end. All right. I'll put my shoe at the end. So every compact set, when you plug it into a continuous function, it turns into another compact set. That's the moral of the story. Can we just tie this into the extreme value theorem? What that means is, how can we demonstrate? So let's use this to show that f has a min and a max, right? Now, remember, what we've just demonstrated is that f of k will be compact. So that means it's closed and bounded, right? By the Heine-Borel theorem. The f of k will be closed and bounded. Does that mean it has a maximum and a minimum? Actually, it does mean that. So first of all, the fact that it's bounded, since it's bounded, it has, you can't say that automatically means it has a maximum element, but it does have a sup. Remember the sup? We haven't talked about the sup much lately, but any bounded set has a sup, the least upper bound. So since it's bounded, it has a sup. But the sup might be outside of the set, in which case it doesn't count as a maximum element. But it's not outside of the set because the set is also closed, all right? The fact that it's closed means that anything that the set approaches is also in the set, because all the limit points are part of the set, which means the sup is automatically part of the set, because the sup is always a value which the set is approaching arbitrarily close to. So since it's bounded, it has a sup. Since it's closed, the sup is in the set. So it's actually a maximum value, right? That's the difference between a sup and a maximum, is sometimes the sup might not be in your original set. But we have explained that actually in this case, the sup really must be in the original set, and that makes it a maximum. So this is why the set has a maximum value. It also has a minimum value because you say the same things about the inf. So I will just say similarly, the min exists because the inf is in the set. The inf exists because it's bounded, and the inf is inside the set because it's closed. Right? This is what we always show something for the sup, and then I just say, yeah, the same thing is true for the inf. I have I suppose I have a pro-sup bias. I never talk about the inf. I always talk about the sup, and then say, yeah, the inf is the same. It's true. Sorry, I'm a supremacist. I just made that up. All right. That's enough of that. We got 6 minutes remaining. Sorry for all the proofs today. I want to talk about what we're going to talk in more detail about next time, but I can give you a little preview. What I want to talk about next is, I don't know if it disappoints you that a lot of the things we discuss are just like things you already knew from calculus, but we're like talking about it like with the epsilons. I don't know if that makes you feel better about talking about the same stuff again. This is actually a concept which only makes sense if you understand about the epsilons. And in the context of a calculus class, you really cannot discuss this concept because it doesn't make sense at all using the standard closer and closer version of continuity. So there is everybody knows about what it means for a function to be continuous. There's actually a stronger kind of a concept which is called uniformly continuous. So some functions are continuous, but some functions are uniformly continuous. And the concept of uniform continuity is something that requires the epsilons to make sense of. You cannot discuss this without talking about the epsilons, which is why you've never heard of it before. So our next sort of big thing to talk about is called uniform continuity. And I will give you the sort of intuitive version of uniform continuity this time, and then we'll talk in more detail about this. You will notice for an ordinary continuous function, the picture you should have in your mind of the epsilon and delta definition, I hope that you have some picture in your mind. I saw a math tweet this weekend by a math graduate student who said it was one of these like dirty confession tweets that people do sometimes, and I think it was a her. I'm going to say her. Maybe I don't know actually. Their dirty confession was, I'm a math graduate student, but I don't really feel like I understand the epsilon delta thing. I just memorized the definition, and like I can still write the proofs fine, just because I remember how to do it. I don't know if any of you feel the same way, but I hope you have some. Here's my. I thought, oh, what a poor soul that is, who just memorized it. This is the picture which you should have in your mind. If I say the function is continuous at C, it means the function, looks like this sort of. I missed the point. It goes through this point, right? Here's the actual point. What it means is there is, no matter how small this kind of horizontal band, I've drawn this picture before, I don't know if you liked it before, you might not like it this time if you didn't, but no matter how small that little band is, this band has radius epsilon, you can always find a similarly small band around the C so that all the values near C in this band end up in this band up here when you plug them into the function. This is the picture that I have in my mind. Although, I will be honest, if someone asks me to write an epsilon and delta proof, I just memorize the definition and I start writing. I don't actually think about this picture every time. But if I'm in the mood for thinking about what it really means, this is how I think of it. This distance down here is delta. All right. And the idea is, no matter how small the epsilon is, you can always find a delta that's small enough so that all this business fits inside the little window up here. All right. Something that we have noticed as we've done these proofs is typically the delta depends on the C. All right, and this is the big thing about uniform continuity. Typically when you do one of these proofs, the proof sort of ends when you say let delta equal whatever, and then you just prove that is the correct choice of delta. I'm telling you, the delta typically depends on the C. For example, what about if I asked you to show that, say, x squared, f of x equal x squared is continuous at C equals 3. All right, how would you do that proof? I'm not going to write out all the details, but the red part would say you'd end up with f of x minus f of c, which in this case would be 9. And then you simplify that. You say this is less than or equal to, or this is just simplifying, first of all. You factor, right? X minus 3, x plus 3. And then you would do that weird little delta less than 1 trick. If delta is less than 1, that means x is less than, x is close to 3, so that means x is less than 4. So x plus 3 is less than 7, and so I could say this is less than or equal to this times 7. And then I say, let delta be the min of 1 and epsilon over 7, where this 7 here comes from that 7 there. All right? I'm here to tell you the delta depends on the C. You don't see a C in the formula down here, but where did this 7 come from? It came from basically that 3 and plugging in this 4 here. Like if I was using a different value of C, if I was proving this whole thing at C equals 4, then this wouldn't be a 7. I mean, the details would be different, and this number here would not be 7 anymore. I'd factor x minus 4, x plus 4. When I say delta less than 1, that means the x is less than 5, and then when I add 4, x plus 4 would be less than 9. I think I would have to use a 9 here if this C was 4, all right? The delta depends on the C. That means that this one, I know it's time to go, this one is not uniformly continuous because the delta depends on the C. So like it is continuous, but as this C moves around, you have to be updating the delta, the size of this little window here. That is not uniform. Uniformly continuous means you can use the same little window all the time, all the way across the board. That's what we're going to talk about in more detail next time. All right, see you then.